What if I told you that light, the very thing allowing you to watch this video right now, doesn't experience time? What if photons streaming from your screen into your eyes exist in a timeless void where the beginning and end of the universe happen simultaneously? Here's something that will shatter your understanding of reality. From light's perspective, if light could have a perspective, it doesn't move at all. The 13.8 billion years since the Big Bang, 0 seconds for a photon. The journey from the sun to your face, instantaneous. Light exists outside of time and space in a way that makes it fundamentally impossible for it to have what physicists call a frame of reference. And here's the twist that makes this even more mind-bending. Despite light having no frame of reference, despite it existing in this impossible state outside normal physics, literally everything in our universe, every measurement, every interaction, every law of physics depends entirely on light behaving exactly the way it does. Light is simultaneously nowhere and everywhere, experiences no time yet defines all time, and this paradox isn't a bug in physics, it's the fundamental operating system of reality itself. By the end of this video, you're going to understand why Einstein called light the absolute, and why this strange property of light means that you, sitting there right now, are connected to every star in the universe in ways you never imagined. But before we dive into this journey, do me a favor, hit that like button and subscribe, because what we're about to explore together will fundamentally change how you see reality. And I'm curious, drop a comment telling me what country you're watching from and what time it is where you are. Because as you'll discover, time itself is far stranger than you think. Let's start with something simple: walking. You're walking down a train platform at 5 miles per hour. The train next to you is moving at 50 miles per hour. From your perspective, the train zooms past you at 45 miles per hour relative to you. Now imagine you're on that train, walking forward at 5 miles per hour. Someone on the platform measures your speed as 55 miles per hour, the train's 50 plus your 5. This is a frame of reference. It's simply the perspective from which you measure motion. And here's what makes sense to our everyday experience. Velocities add up. You throw a ball forward from a moving car, and the ball's speed is the car's speed plus your throwing speed. This is called Galilean relativity, named after Galileo Galilei, who formalized these ideas in the 1600s. Your frame of reference is like your personal coordinate system, a way of measuring where things are and how fast they're moving relative to you. If you're sitting still reading a book, that book is stationary in your frame of reference. But someone driving past sees you and that book moving at whatever speed their car is traveling. Every object with mass can have a frame of reference. The Earth has one. Your car has one. You have one. Even a speeding bullet has a frame of reference. From the bullet's perspective, it's sitting still while the world rushes toward it at incredible speed. Think of it like this. A frame of reference is like a camera. You can mount a camera on a car, on a train, on a rocket ship, and from each camera's viewpoint, the world looks different. The math changes, the measurements change, but the underlying physics remains consistent. Here's where things get interesting. Isaac Newton believed there was an absolute frame of reference, a universal stage on which all motion happened. He imagined absolute space and absolute time, unchanging and uniform throughout the universe. In Newton's universe, time ticked at the same rate everywhere, and space was just empty geometric grid. But in 1887, two scientists named Albert Michelson and Edward Morley accidentally destroyed this comfortable worldview. They were trying to measure Earth's motion through what scientists called the luminiferous ether, a hypothetical substance that permeated all of space and supposedly carried light waves, the way water carries ocean waves. The Michelson-Morley experiment was brilliant in its simplicity. They shot light beams in different directions and measured whether light traveled faster when moving with Earth's motion through the ether or against it. Think of it like swimming downstream versus upstream. You'd expect light to move faster in one direction if it was moving through some medium. The result? Light traveled at exactly the same speed in all directions. No difference, none, zero. This shouldn't have been possible. If light needed a medium to travel through, and Earth was moving through that medium, there had to be a difference. It would be like measuring the speed of sound while sitting in a moving car and finding it's exactly the same in all directions impossible. Because sound waves do travel through air, and your motion through air affects measurements. Scientists were baffled. Some proposed that maybe Earth dragged the ether with it. Others suggested that objects physically contracted when moving through the ether, making the measurements appear the same. The physics community spent nearly 2 decades grasping for explanations. Then, in 1905, a 26-year-old patent clerk named Albert Einstein published a paper that changed everything. But here's what most people don't know. Einstein wasn't trying to explain the Michelson-Morley experiment. He was thinking about a deeper problem: electromagnetic theory and motion. Einstein asked a deceptively simple question. What would you see if you could ride alongside a light beam, traveling at the speed of light? According to classical physics, you should see the light wave frozen in space, oscillating but not moving. But Maxwell's equations, the fundamental laws of electromagnetism, didn't allow for stationary light waves. They only worked for light moving at one specific speed. This thought experiment, which Einstein first conceived as a teenager, led him to a radical conclusion. Maybe light always travels at the same speed relative to everyone, regardless of their motion. Maybe the speed of light isn't relative, maybe it's absolute. Here's where your brain is about to bend. Einstein proposed that the speed of light in a vacuum, approximately 299,792,458 meters per second, is the same for all observers, regardless of their motion or the motion of the light source. Let that sink in. You're standing still. You measure light at 299,792,458 meters per second. You're in a rocket ship traveling at half the speed of light. You measure light at the same speed. Someone in a rocket ship traveling at 99.9%. The speed of light measures it at the exact same speed. This violates everything we know from everyday experience. If you're on a train going 50 miles per hour and you walk forward at 5 miles per hour, someone on the platform sees you moving at 55 miles per hour. But if that train is moving at half the speed of light and you shine a flashlight forward, the light doesn't travel at light speed plus train speed. It still travels at exactly light speed. How is this possible? Einstein's answer was breathtaking. Time and space aren't fixed. They bend, stretch, and compress to ensure that light always measures the same speed for everyone. This is the core of special relativity. To make the speed of light constant, time must slow down as you move faster. Space must contract in the direction of motion. These aren't optical illusions. They're real, measurable changes to the fabric of reality itself. Hendrik Lorentz had actually worked out the mathematical transformations that described these effects before Einstein, but he thought they were just corrections for motion through the ether. Einstein realized they were fundamental properties of spacetime itself. Time dilation and length contraction aren't side effects. They're how the universe maintains light's constant speed. Let me give you an analogy. Think of it like a speed limit enforced by the universe itself. But instead of getting a ticket when you break the speed limit, the universe changes time and space around you to make sure you can never break it. The faster you try to go, the more time slows down for you and the more space contracts ahead of you, ensuring light always beats you to the finish line. In 1971, physicists Joseph Haffel and Richard Keating proved this wasn't just theoretical. They flew atomic clocks around the world on commercial airplanes, some eastward, some westward. When they compared these clocks to identical clocks that stayed at the U.S. Naval Observatory, the flying clocks showed different times. The eastward flying clock lost about 59 nanoseconds. The westward flying clock gained about 273 nanoseconds. These weren't measurement errors. These clocks had literally experienced less time due to their motion. Time itself had slowed down for them. But here's what will blow your mind. This means that astronauts on the International Space Station, orbiting at 17,500 miles per hour, age slightly slower than people on Earth. Not much, about 0.007 seconds per 6-month mission. But it's real. They're literally time travelers, experiencing less time than the rest of us. Now imagine something moving even faster. Muons are subatomic particles created when cosmic rays hit Earth's upper atmosphere, about 15 kilometers up. These muons decay with a half-life of 2.2 microseconds. At near light speed, they should only travel about 660 meters before half of them decay. But we detect muons at sea level. They're making the full 15-kilometer journey. How? From our perspective, time dilation. The muons are moving so fast that time slows down for them. Their internal clocks run slower, so their 2.2 microsecond half-life stretches to nearly 44 microseconds from our perspective, plenty of time to reach the ground. But here's the perspective flip that makes this even stranger. From the muon's frame of reference, it's not experiencing any time dilation at all. Its clock runs normally. Instead, the distance it needs to travel contracts. The 15-kilometer atmosphere compresses to just 660 meters due to length contraction. Same result, different explanation, depending on your frame of reference. Every frame of reference is equally valid. The muon's experience is just as true as ours. Neither perspective is more real than the other, except for light. Light doesn't get to have this perspective. Let's talk about the Lorentz transformations, the mathematical equations that tell us how time and space change between different frames of reference. Don't worry, I'll keep this intuitive. When you want to transform measurements from one moving frame to another, you use what's called the Lorentz factor, often written as gamma. Gamma. The formula is gamma equals 1 square root 1, v squared per c squared, where v is your velocity and c is the speed of light. At everyday speeds, this factor is essentially 1, meaning no noticeable time dilation or length contraction. When you're driving at 60 miles per hour, gamma equals 1.0000000000001, basically 1. Time dilation and length contraction are happening, but they're utterly negligible. But as you approach the speed of light, something dramatic happens. At 50% of light speed, gamma equals about 1.15, you'd experience 15% time dilation. At 90% of light speed, gamma equals 2.29, time runs more than twice as slow for you. At 99% of light speed, gamma equals 7.09. Watch what happens as we get even closer. At 99.9% of light speed, gamma equals 22.4. At 99.99%, it's 70.7. The closer you get to light speed, the more extreme these effects become. Now here's the critical moment. What happens when v equals c? When your velocity equals the speed of light? Look at the equation. You get 1 square root 1 to 1, which equals 1/0, which equals 1/0. Division by 0. Mathematical impossibility. Infinity. The Lorentz factor becomes infinite at the speed of light. Time dilation becomes infinite. Length contraction becomes infinite. The equations that transform between frames of reference literally break down. Think of it like this. The Lorentz transformations are a mathematical bridge between frames of reference. You can build that bridge between any two massive objects moving at any speed less than light. But when you try to build a bridge to light itself, the bridge extends infinitely and never reaches its destination. From a photon's frame of reference, if such a thing could exist, time would be infinitely dilated, zero time would pass. The entire journey from emission to absorption would happen in exactly 0 seconds. The photon wouldn't experience duration. Similarly, length contraction would be infinite. The entire universe in the direction of motion would contract to exactly 0 distance. From the photon's perspective, all points along its path exist at the same location. But wait, it gets stranger. Not only would time and space become meaningless, but so would causality, motion, and change. A photon exists in a state where its emission and absorption are simultaneous. The birth and death of the universe happen at once. Past, present, and future collapse into a single moment. This isn't just impractical to imagine, it's fundamentally undefined. Physicists don't say light's frame of reference is weird or hard to understand. They say it doesn't exist. It's not a valid frame of reference in special relativity. Brian Greene, a theoretical physicist at Columbia University, puts it this way. From a photon's perspective, the question, what does the universe look like, is meaningless because there is no perspective to speak from. The photon's frame is not part of the architecture of spacetime. Here's an analogy. Imagine trying to take a photograph of your camera from that camera's perspective. You can photograph the camera in a mirror. You can photograph another camera with that camera, but you cannot photograph the camera from its own lens, looking at itself. The request is inherently self-contradictory. Similarly, you cannot describe physics from light's frame of reference, because the very notion of a frame of reference requires time to pass and space to exist. For light, neither exists. But this raises a profound question. If light has no frame of reference, if it exists outside the normal rules of spacetime, how does it interact with anything? How does it carry energy and momentum? How does it allow us to see and measure and exist? Now let's talk about why you can never reach the speed of light. And this isn't just about needing a really powerful rocket engine. It's about the fundamental structure of reality. Remember that Lorentz factor? As you accelerate closer and closer to light speed, two things happen simultaneously. Time slows down for you, and your mass, or more accurately, your relativistic mass increases. The faster you go, the more massive you become from an outside observer's perspective. This isn't about gaining matter. It's about energy and mass being equivalent, as Einstein showed in his famous E=mc. The energy you're putting into acceleration gets converted into increased mass. At 90% of light speed, your relativistic mass is about 2.3 times your rest mass. At 99%, it's 7 times. At 99.9%, it's 22 times. And as you approach light speed, your mass approaches infinity. Here's why this matters. Force equals mass times acceleration. To accelerate something, you need to apply force. But if that something's mass keeps increasing the faster it goes, you need more and more force to continue accelerating it. Think of it like pushing a snowball uphill. As it rolls, it accumulates more snow, hitting heavier. The faster it goes, the more snow it picks up, the harder it becomes to push. Now imagine that snowball's mass approaches infinity as it approaches a certain speed. You'd need infinite force to reach that speed. This is why the Large Hadron Collider, the most powerful particle accelerator ever built, can smash protons together at 99.999999991% of light speed, but can never quite reach 100%. They pump enormous amounts of energy into those protons. Each proton at top speed has about 7,000 times its rest energy. But that energy just makes the protons more massive, not faster. CERN scientists have calculated that to accelerate a single proton to exactly the speed of light would require infinite energy, not a lot of energy. Not more energy than exists in the universe. Literally infinite energy, which doesn't exist. But here's the beautiful part. Photons don't have this problem because they have no rest mass. 0. A photon at rest doesn't exist. There's no such thing. Photons are always moving at the speed of light from the moment they're created. They don't accelerate from 0 to light speed. They simply exist at light speed. This is deeply weird. Every object you've ever encountered can be at rest in some frame of reference. Your phone can sit motionless on a table. A car can be parked. A planet can be still relative to its sun. But a photon? Never at rest. Not in any frame. It's moving at sea from every perspective. Always, forever. Here's an analogy. Imagine a shark. Sharks must keep moving or they die. They need water flowing over their gills to breathe. But they can slow down, they can rest at the bottom, they can adjust their speed. Now imagine a creature that doesn't just need to move, but is defined by moving at one specific speed. It's not that it can't stop. The concept of stopping doesn't apply to it. Its existence is its motion. That's a photon. Carlo Rovelli, an Italian theoretical physicist, describes it beautifully. A photon is not a little bullet traveling through space. A photon is a quantum of energy being transferred at the speed of light. The motion isn't something the photon does. The motion is what the photon is. Now here's something that will mess with your intuition. Since you can never reach light speed, and light is always moving at light speed relative to you, this means there's an unbridgeable gap between you and light. No matter how fast you go, light always moves away from you at exactly c. Imagine you're in the fastest spaceship ever conceived, accelerating constantly. You're now going 99.9999999% of light speed. You shine a flashlight forward. That light moves away from you at 299,792,458 meters per second. Someone on Earth, watching you zoom past, also measures that light at 299,792,458 meters per second. The person on Earth sees you moving at nearly light speed, yet the light is still pulling away from you at full light speed from your perspective. This isn't just counterintuitive. It's reality telling us something profound about the structure of the universe. There's a fundamental, unbridgeable division between things with mass and massless particles like light. We exist in time. Light doesn't. We can be at rest. Light cannot. We have frames of reference. Light does not. And yet, paradoxically, we're completely dependent on light for our existence. Let's follow the life of a photon from your perspective and from its own impossible perspective. A photon is born in the core of the sun. Nuclear fusion hydrogen atoms fusing into helium releases tremendous energy. That energy manifests as high-energy gamma-ray photons. These photons immediately begin colliding with the dense plasma in the sun's core, getting absorbed and re-emitted countless times. A single photon's journey from the sun's core to its surface takes somewhere between 10,000 to 170,000 years, depending on whose calculations you trust. It's a random walk, bouncing around, constantly absorbed and re-emitted in different directions. The sun's core is so dense that light travels only a fraction of a millimeter before hitting something. Eventually, after millennia of this pinball game, a photon escapes the sun's surface and streams into space. From your perspective on Earth, this photon takes 8 minutes and 20 seconds to travel the 93 million miles from the sun to your eyes. You step outside, and that photon born tens of thousands of years ago in the sun's core, freed from the sun's surface 8 minutes ago, enters your eye. It strikes a rhodopsin molecule in a rod cell in your retina. The photon's energy triggers a chemical change. That rhodopsin molecule changes shape, starting a cascade of signals that travel through your optic nerve to your brain. The photon has been absorbed. It no longer exists. Its energy has been transferred, converted into chemical and electrical signals that become your experience of seeing sunlight. From your frame of reference, this photon had quite a journey. Tens of thousands of years inside the sun, 8 minutes through space, and then it ended by giving you sight. But from the photon's frame of reference, 0 time elapsed. The moment of its creation in the sun's core and the moment of its destruction in your eye happened simultaneously. The photon didn't experience duration, didn't experience travel, didn't experience its journey through space. In fact, due to infinite length contraction, the distance from the sun to your eye was 0 from the photon's perspective. It was emitted and absorbed at the same location in its frame. Here's what's genuinely mind-blowing. This applies to all photons, regardless of how far they travel from our perspective. The photons reaching us from the edge of the observable universe, traveling for 13.8 billion years, crossing 46 billion light years of expanding space experienced 0 time. From their perspective, they were emitted and absorbed simultaneously at the same location. Think about that. The oldest light in the universe, carrying information from the cosmic microwave background radiation just 380,000 years after the Big Bang, has experienced exactly as much time as the light from your phone screen, 0. Kip Thorne, the Nobel Prize-winning physicist who consulted on the movie Interstellar, explains it this way. Photons are the messengers of the universe, carrying information across vast distances. But they themselves never experience the journey. They exist in an eternal moment. This has profound implications. When you look at distant galaxies through a telescope, you're seeing them as they were millions or billions of years ago. The light is old from your perspective, but that light itself hasn't aged. It's the same age as light that just left your lamp a nanosecond ago. Here's another way to think about it. Imagine you're watching a movie. From your perspective, the movie has a beginning, middle, and end. It takes 2 hours to watch. But imagine a character in that movie who exists only in one frozen frame. From their perspective, the entire movie beginning to end exists simultaneously. They don't experience the sequence of events because they exist outside the flow of the movie's time. That's a photon. It exists in one frozen moment where emission and absorption are simultaneous. But here's the paradox that should be making your head hurt. If photons experience no time, how do they carry information? How does light from distant stars tell us about events that happened billions of years ago? How can light have a wavelength, which is inherently a property that requires distance and time? The answer is shocking. All these properties exist for us, not for the photon. Wavelength, frequency, energy, these are properties we measure when light interacts with our frame of reference. The photon doesn't have these properties in its own frame. They only exist in the context of its relationship to us. Light is fundamentally relational. Its properties only exist in the interaction between the photon and things with mass, things that exist in time, things that have frames of reference. This is why physicists say light has no frame of reference. It's not just that the math breaks down, it's that light doesn't exist for itself. It only exists in relation to us. Now we arrive at the central paradox of this video. Light has no frame of reference, yet everything in physics depends on light behaving exactly as it does. Let's start with measurement. How do you measure distance? At its most fundamental level, you're using light. A ruler? That works by reflecting light into your eyes. A laser rangefinder? Sends light and measures how long it takes to return. GPS calculates position based on the time it takes for light-speed radio signals to reach your phone from satellites. In 1983, scientists made a radical decision. They redefined the meter, the fundamental unit of distance, not as a physical object, but in terms of light. 1 meter is now defined as the distance light travels in 1/299th, 792,458 of a second. Think about what this means. We've made light's speed the definition of distance itself. We didn't measure light's speed in meters per second and discover it was 299,792,458 meters per second. We decided that whatever distance light travels in 1/299th, 792,458 of a second is, by definition, 1 meter. Why? Because light speed is more constant than anything else we can measure. More constant than the distance between atoms in a metal bar. More constant than the vibrations of any atomic clock. Light speed is the most reliable constant in the universe. So we built our entire system of measurement on top of it. But it goes deeper. Every interaction in the universe, every force, every push, every pull is mediated by particles. And the fundamental mediator of electromagnetic force is the photon. When you touch a table, you feel solid matter. But you're not actually touching anything. The electrons in your hand and the electrons in the table are repelling each other via electromagnetic force. And electromagnetic force is carried by virtual photons, photons that exist briefly in the quantum foam, mediating the repulsion between charged particles. When you see, you're detecting photons. When you feel heat, you're experiencing infrared photons. When your radio picks up a signal, it's responding to radio wave photons. Even the electromagnetic force holding atoms together, that's mediated by photons. Richard Feynman, one of the greatest physicists of the 20th century, developed quantum electrodynamics, QED, the theory of how light and matter interact. He won the Nobel Prize in 1965 for this work. Feynman showed that all electromagnetic interactions can be described as the exchange of photons. Here's his famous summary. All of the phenomena of nature, except for gravity, can be reduced to the exchange of photons. Let that sink in. Chemistry? Photon exchanges. Biology? Photon exchanges making chemistry work. Your thoughts? Electrical signals in neurons, mediated ultimately by photon exchanges. The stability of matter itself? Electromagnetic forces keeping atoms together, all photon mediated. Literally everything you experience except gravity is at a fundamental level about light. Here's an analogy. Imagine a massive computer network. Every computer represents matter electrons, protons, atoms. Every message between computers represents an interaction. And light? Light is the fundamental protocol, the TCP/IP of the universe that makes all communication possible. But unlike TCP/IP, which we invented and could replace, light's role is hardwired into reality itself. The universe doesn't just use SE, light as its messenger. The universe's fundamental structure depends on light behaving exactly as it does. Max Planck discovered in 1900 that light comes in discrete packets quanta, which we now call photons. This was the birth of quantum mechanics. Einstein explained the photoelectric effect in 1905 by showing that light behaves as particles. These discoveries didn't just advance physics. They revealed that light is fundamental to the quantum nature of reality. The speed of light appears in equations throughout physics, often as c. But c doesn't just mean the speed of light. In a deeper sense, c represents the maximum speed of causality itself, the fastest that cause and effect can propagate through spacetime. When Einstein developed his famous equation E equals mc, the c squared in that equation isn't just about light. It's about the fundamental conversion rate between energy and mass, between matter and pure energy. That conversion rate happens to be set by light speed, but it's more profound than just light is fast. Light speed is the speed limit of reality. It's the speed at which information can travel, the speed at which cause can lead to effect, the speed at which change can propagate through the universe. If light's speed were different even slightly, the entire structure of reality would collapse. Stars wouldn't form properly. Atoms would be unstable. Chemistry wouldn't work. Life couldn't exist. The anthropic principle suggests that we observe the constants of nature to be what they are, because if they were different, we wouldn't be here to observe them. The speed of light is one of those constants. It's not arbitrary, It's precisely what it needs to be for a universe like ours to exist. And yet this fundamental constant, this cosmic speed limit, this universal messenger upon which everything depends, it experiences none of it. Light makes everything possible, while existing outside of everything it enables. Now let's make this even stranger by diving into light's quantum behavior. You might have heard that light behaves as both a particle and a wave. This is the famous wave-particle duality, and it's even weirder than most people realize. The double-slit experiment, first performed by Thomas Young in 1801, remains one of the most mind-bending demonstrations in all of physics. Here's how it works. You have a light source, a barrier with two slits, and a screen behind it. When you shine light through both slits, you get an interference pattern on the screen alternating bright and dark bands. This is classic wave behavior, like ripples in water interfering with each other. But here's where it gets strange. This interference pattern appears even if you send one photon at a time through the apparatus. One single photon somehow interferes with itself, passing through both slits simultaneously and creating an interference pattern over time. But if you try to observe which slit each photon goes through, if you put a detector at one slit to watch, the interference pattern disappears. The photons start behaving like particles, going through one slit or the other, and you just get two bright bands on the screen instead of an interference pattern. The act of observation changes light's behavior. It's not that we're clumsily disturbing the photons with our measurement quantum mechanics says that the photon genuinely doesn't have a defined path until we measure it. It exists in a superposition, literally taking both paths simultaneously until observation collapses it into one path or the other. Here's what this means for light's frame of reference. Not only does light experience no time or space, but it doesn't even have a determined path through that non-existent space until it interacts with something. John Wheeler, one of the most creative physicists of the 20th century, proposed an even stranger version of this experiment in 1978 called the delayed choice experiment. The idea is to decide whether to observe which slit the photon went through a FTE, or the photon has already passed through the slits, but before it hits the screen. This experiment has been performed, and the results are mind-blowing. Your choice of whether to measure the photon's path determines retroactively whether it behaved as a wave or particle. The photon's past behavior depends on your future choice. Think about what this means. The photon exists in a superposition of all possible paths. It doesn't choose which path to take until the observation is made. And since the photon experiences no time, the when of this choice is meaningless from its perspective. From the photon's timeless viewpoint, its emission, its journey, its path, and its absorption all happen simultaneously. Your choice to observe it doesn't happen after its journey in any absolute sense. It's all one simultaneous event in the photon's frame that doesn't exist. Quantum entanglement makes this even more bizarre. When two photons are entangled created together in a certain way, they remain correlated no matter how far apart they travel. Measure the polarization of one photon, and you instantly know the polarization of the other, even if it's on the other side of the galaxy. Einstein hated this. He called it spooky action at a distance, and thought it proved quantum mechanics was incomplete. But in 1964, physicist John Bell developed a mathematical test to determine whether this correlation could be explained by hidden variables or required actual spooky connections. Experiments testing Bell's inequalities, particularly those by Alling aspect in the 1980s, and more recently experiments that won the 2022 Nobel Prize in Physics, have confirmed that quantum entanglement is real. The correlations between entangled photons are stronger than any local hidden variable theory could explain. But here's the key. This correlation doesn't involve information traveling between the photons. Nothing moves faster than light. Instead, entangled photons share a quantum state, and measuring one instantaneously determines the state of both. From our perspective, with our frame of reference, this looks like instantaneous correlation across vast distances. But from the photon's non-existent frame of reference, both photons are emitted and absorbed at the same moment at the same location. There's no distance between them, no time between their measurements. The correlation isn't mysterious from their timeless, spaceless viewpoint. There's nothing to correlate across because there's no separation. Here's an analogy. Imagine tearing a photograph in half. You mail one half to Australia and keep one half. When you look at your half and see the left side of someone's face, you instantly know the other half shows the right side. This isn't information traveling between the halves. It's the consequence of them being parts of a whole. Entangled photons are like that, except the photograph exists outside of space and time from the photon's perspective. They were never separate in any frame that they could experience. Quantum mechanics tells us that light isn't just a wave or a particle, it's a quantum field. Photons are excitations of the electromagnetic field, ripples in this fundamental field that permeates all of space. When we create a photon, we're exciting this field. When we destroy a photon, we're calming it back down, and this field doesn't experience time. The entire electromagnetic field, in some sense, exists in a timeless state. Causality and temporal ordering are properties that emerge when the field interacts with matter, with things that have mass, with things that exist in time. The deeper we look at light's quantum behavior, the more we find that light's lack of a frame of reference isn't just a mathematical curiosity. It's fundamental to how light makes quantum mechanics work. Now let's bring this back to you. Everything we've discussed seems abstract relativistic physics, quantum mechanics, frames of reference. But light's strange nature directly affects how you experience reality right now. Look around you. Everything you see is light. But you're not seeing things as they are. You're seeing them as they were when light left them. The computer screen in front of you, you're seeing it as it was a few nanoseconds ago. The wall across the room, as it was several nanoseconds ago. The moon, as it was 1.3 seconds ago. The sun, as it was 8 minutes and 20 seconds ago. You exist in a bubble of delayed information. You never see. Now you only see the past because light takes time to reach you. But here's the profound part. From the photon's perspective, there is no delay. The moment the light left the sun and the moment it entered your eye are the same moment. The photon carrying information from a distant galaxy and its absorption in a telescope happens simultaneously in the photon's non-frame. You are, quite literally, in direct temporal contact with everything you can see. Not in your frame of reference, but in light's timeless existence. When a photon from a distant star enters your eye, that photon bridges 13 billion years of time from your perspective, but 0 time from its own. You're touching that ancient star in a very real sense. Think of it like this. You're an island in an ocean of time. Light is a bridge that connects you to every other island, but the bridge itself exists outside the ocean. The bridge doesn't experience the crossing. It simultaneously touches both shores. This changes how you should think about looking at the night sky. When you see the Andromeda galaxy, 2.5 million light years away, you're not just seeing old light from a distant place. You're participating in a timeless connection. The photons that left Andromeda 2.5 million years ago, from your perspective, and the photons entering your eye right now are experiencing the exact same eternal moment. Every human who has ever looked at Andromeda has shared that same timeless moment with it. Every human who ever will look at it will share it too. Light creates a timeless network connecting all observers to all observed things. Your brain doesn't construct reality from instantaneous snapshots. It constructs reality from delayed light signals. Your sense of now is actually a patchwork of different thens, stitched together by your brain into a coherent experience. When you look at your hand holding your phone, the light from your hand takes infinitesimally longer to reach your eyes than the light from your phone screen, because your hand is slightly farther away. Your brain corrects for this, constructing a unified present moment from light that left different places at slightly different times. Your reality is built from light, and light exists outside of time. So in a strange way, your experience of now is constructed from information that the universe considers timeless. Here's something even more personal. Every interaction in your body, every nerve signal, every muscle contraction, every thought in your brain is mediated by electromagnetic forces, which are carried by photons. Virtual photons, constantly being exchanged between charged particles, are what make you possible. You are, in a very literal sense, held together by light. Your atoms don't fly apart because electromagnetic forces keep them bound, and those forces are photons doing their work. When you feel the warmth of sunlight on your skin, you're not just feeling heat, you're feeling photons from the sun being absorbed by your molecules. Those photons were created in nuclear fusion reactions 93 million miles away, fought their way out of the sun over thousands of years, crossed empty space in 8 minutes, and then gave their existence, their energy to warm you. And from their perspective, they were created and destroyed in the same instant. Your warmth, from their timeless viewpoint, is simultaneous with their birth in the sun. This should fundamentally change how you think about yourself and your place in the universe. You're not separate from distant stars and galaxies. You're connected to them by light, and light doesn't experience the separation that you do. When you look up at the night sky, you're not just observing the universe, you're participating in it. The light entering your eyes creates a timeless link between you and ancient, distant places. You are part of a cosmic web of light, connecting everything that can see to everything that can be seen. David Deutsch, a physicist at Oxford, puts it this way: every time you open your eyes, you're receiving messages that have traveled through space and time, but the messengers themselves are outside of time. You're reading timeless letters from the universe. And here's the most beautiful part. You are made of atoms that were forged in the hearts of stars. Those atoms were scattered through space when those stars died. They coalesced into our solar system, our planet, and eventually you. And every step of that journey, every formation of atoms, every chemical reaction, every biological process that led to you, all of it mediated by light. You are stardust held together by light, perceiving the universe through light, connected to everything by light. Let's zoom out to the largest scales possible and see how light's strange properties affect our understanding of the entire universe. General relativity, Einstein's 1915 theory of gravity, describes gravity not as a force, but as the curvature of spacetime. Massive objects bend spacetime, and light follows that curvature. Light doesn't experience gravity pulling on it. Light follows the straightest possible path through curved spacetime. This has been confirmed countless times. During a solar eclipse in 1919, Arthur Eddington measured the positions of stars near the sun and found they appeared shifted. The sun's mass was bending the spacetime around it, causing light from distant stars to follow curved paths. This was the first major confirmation of general relativity. Today we see this effect much more dramatically in gravitational lensing. When light from a distant galaxy passes near a massive object like a galaxy cluster, the space-time curvature bends the light's path, creating multiple distorted images of the background galaxy. Some of the most stunning Hubble and James Webb Space Telescope images show gravitational lensing in action arcs and rings of light bent around massive objects. But here's what's profound. Light defines the structure of spacetime itself. The paths that light takes through spacetime, called null geodesics, are the boundaries of causality. They define what events can influence what other events. Spacetime is described mathematically as having a light cone structure. From any event, light expanding outward in all directions traces out a cone in four-dimensional spacetime. Events inside your future light cone can potentially be affected by you. Events outside your light cone cannot not yet, because information from you can't reach them faster than light. The entire causal structure of the universe, what can affect what can be connected to what, is determined by light's path through spacetime. But remember, light itself doesn't experience this journey. From a photon's perspective, it doesn't travel along these geodesics because it doesn't experience travel at all. The geodesic, the light cone, the causal structure, these are all properties of spacetime as experienced by massive objects, not by light itself. Light defines the shape of spacetime without experiencing that shape. The observable universe, the portion of the universe we can possibly see, is defined by light. It's a sphere with a radius of about 46 billion light years, which is how far light has been able to travel since the Big Bang 13.8 billion years ago. The size is larger than n, 13.8 billion light years due to cosmic expansion. Beyond that sphere, we cannot see. Not because there's nothing there, but because light from those regions hasn't had time to reach us yet. Our observable universe is literally defined by where light has been able to travel. And from those photons' perspective, the ones that have traveled the farthest, carrying information from the edge of the observable universe, they experienced zero journey time. They were emitted at the Big Bang and absorbed in our telescopes in the same timeless instant. The cosmic microwave background radiation is particularly fascinating. This is light that was emitted about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons could finally travel freely. Before this moment, the universe was opaque. Photons couldn't travel without immediately running into charged particles. This radiation is now stretched by cosmic expansion into microwaves, and it comes at us from all directions. It's the oldest light we can observe, a snapshot of the infant universe. But from those photons' perspective, they were released 13.8 billion years ago, our time, and arrived in our detectors today, our time, but they experienced zero time. The infant universe and today are the same moment for them. Cosmologists like Stephen Hawking spent their careers studying light's behavior near extreme space-time curvatures. Near black holes, space-time is curved so severely that light itself can barely escape. The event horizon, the boundary of a black hole, is defined by light. It's the surface where light's geodesics are bent so sharply that they can never escape. Inside the event horizon, all light paths lead inward. This isn't because light is pulled by gravity. It's because space-time itself is curved so severely that the straight paths light must follow all point toward the singularity. And yet, even here, light itself experiences none of this. A photon falling into a black hole doesn't experience being trapped or falling or approaching the singularity over time. From its non-perspective, it's emitted and absorbed simultaneously, whether that absorption happens in your eye or in a black hole's singularity. Hawking radiation, a theoretical radiation that black holes emit, involves photons being created at the event horizon through quantum effects. These photons define whether a black hole grows or shrinks. Light, existing outside of time, determines the fate of objects whose gravity is so strong that time itself breaks down near them. The expansion of the universe itself is measured by light. Edwin Hubble, in 1929, discovered that distant galaxies show redshift. Their light is stretched to longer wavelengths, indicating they're moving away from us. The farther away a galaxy is, the faster it's receding, because space itself is expanding. We measure cosmic expansion by analyzing light. The redshift tells us how much the universe has expanded since that light was emitted. Every photon from a distant galaxy carries in its wavelength a record of the universe's expansion history. But the photon doesn't experience that expansion. It doesn't gradually redshift during its journey from its own perspective. It's emitted at one wavelength and absorbed at a different wavelength, simultaneously, with the difference being a property of the expanding spacetime it connects, not something it experiences. Light is the measuring tape of the cosmos, defining distances, defining causality, defining the observable universe itself, all while existing outside the very fabric it measures. Now let's tackle one of the most confusing aspects of light. How can something with zero mass carry energy and momentum? Einstein's famous equation E equals mc seems to say energy equals mass times the speed of light squared. If photons have zero mass, shouldn't they have zero energy? The answer is that E equals mc is actually a simplified version of a more complete equation. E squared equals mc squared squared plus pc squared, where p is momentum and m is rest mass. For objects at rest, p equals 0, so you get E equals mc. But photons are never at rest. They have zero rest mass, but non-zero momentum. So for photons, the equation becomes simply E equals pc. Photons do have energy. Lots of it. The energy of a photon is given by E equals hf, where h is Planck's constant and f is frequency. High-frequency photons like gamma rays have tremendous energy. Lower-frequency photons like radio waves have less energy, but they still have some. This energy can do real work. Solar panels convert photon energy into electricity. Photosynthesis converts photon energy into chemical energy in plants. Your skin absorbs photon energy and converts it to heat. Gamma rays can damage DNA with their energy. Photons also carry momentum. When light hits a surface, it exerts pressure radiation pressure. This is tiny under normal conditions, but it's real and measurable. In space, where there's no air resistance, radiation pressure from sunlight is significant enough to affect spacecraft trajectories. NASA has to account for solar radiation pressure when calculating orbits. Some scientists have proposed solar sail spacecraft propelled entirely by light pressure. In 2018, Japan successfully deployed Icarus, the first spacecraft to successfully demonstrate solar sail propulsion. It accelerates by reflecting photons, using the momentum transfer from sunlight hitting its reflective. Massless particles with no frame of reference can push a spacecraft. The photons themselves experience no time, no distance, no journey, yet they transfer real momentum to massive objects, causing real acceleration over time and distance. Here's an analogy. Imagine a river current. The current itself has no mass. It's just the motion of water. But it can push a boat, transfer momentum, do work. Photons are like that, except even stranger, because they're not motion of something else. They're pure energy in motion with zero rest mass. Arthur Compton won the Nobel Prize in 1927 for demonstrating that photons carry momentum. In the Compton effect, X-ray photons collide with electrons and lose energy, decrease in frequency, while the electrons recoil. This is exactly like a collision between two billiard balls, except one ball is a massless photon. The photon transfers momentum to the electron gains kinetic energy, and the photon loses energy. This only makes sense if photons have momentum, despite having no mass. But here's the paradox. Momentum is classically defined as mass times velocity. If mass is zero, momentum should be zero. But quantum mechanics tells us photons have momentum p equals E cos E c equals h lambda, where lambda is wavelength. Photons have momentum that depends on their wavelength, not their mass. Shorter wavelength means higher momentum. This is purely quantum behavior. It only makes sense in the framework of quantum field theory. From our frame of reference, we can describe photons as having wavelength, frequency, energy, and momentum. We can track their paths, measure their properties, use them to do work. But from the photon's non-existent frame of reference, none of these properties exist for the photon. They only exist in the photon's relationships with other things, with atoms that emit them, with electrons that absorb them, with observers who measure them. A photon is not a little particle carrying properties as it travels. A photon is a quantum of electromagnetic field, a relationship between one point in spacetime, emission, and another point, absorption. With the relationship having specific mathematical properties we interpret as energy, momentum, and wavelength. The photon doesn't have these properties during its journey because there is no during for the photon. It exists as an irreducible connection between emission and absorption, a line in spacetime that doesn't experience the spacetime it connects. Roger Penrose, the Nobel Prize-winning physicist and mathematician, describes it this way. A photon is not a thing that moves through space over time. A photon is a mathematical object that describes a correlation between two events, emission and absorption. The journey is a description from an external frame, not an experience of the photon. This gets even stranger when you consider virtual photons, the photons, that mediate electromagnetic force, but are never directly observed. When two electrons repel each other, physicists describe this mathematically as the exchange of virtual photons between them. Virtual photons exist even more tenuously than regular photons. They violate energy conservation for brief moments, allowed by Heisenberg's uncertainty principle. They borrow energy from the quantum vacuum and must pay it back quickly. These virtual photons have no definite energy or momentum. They exist in quantum superpositions. They're not traveling through space in any classical sense. They're mathematical descriptions of how electromagnetic force propagates. And yet, these virtual photons are what hold atoms together. They're what keep you from falling through your chair. They're the messengers of chemistry, of biology, of every structure in your body. Real photons, massless and timeless, carry energy across the universe. Virtual photons, even more ephemeral, hold the universe together. Both types exist outside any frame of reference, yet both are absolutely essential to everything that does have a frame of reference. Let's dig deeper into why c, the speed of light, is really the speed of causality, the cosmic speed limit for cause and effect itself. In special relativity, space-time is divided by light into three regions relative to any event. The past light cone, events that could have caused this event. The future light cone, events this event could cause. And the elsewhere, events that are space-like separated and cannot have causal connection. If you draw a space-time diagram with time on the vertical axis and space on the horizontal axis, and you mark a single event, light expanding from that event traces out a cone shape. Everything inside your past light cone could have affected you. Everything inside your future light cone could be affected by you. Everything outside both cones is causally disconnected from you. Nothing you do now can affect those events, and those events cannot affect you now. This isn't just about light, it's about any influence. Gravity waves travel at light speed. Information cannot travel faster than light. Cause cannot propagate faster than light. When you flip a light switch, the light bulb doesn't turn on instantly. The electromagnetic signal travels down the wire at close to light speed, actually about 50 to 99% of light speed in typical wires, due to the properties of the wire material. The light bulb turns on a fraction of a nanosecond after you complete the circuit. For everyday distances, this is unnoticeable. But for cosmic distances, it matters profoundly. When the sun suddenly disappeared, hypothetically, we wouldn't know for 8 minutes and 20 seconds, not just the light gravity too. Earth would continue orbiting the sun's now empty location for 8 minutes and 20 seconds until the gravitational change propagated to us at light speed. In 2017, LIGO detected gravitational waves from two neutron stars colliding 130 million light-years away. About 1.7 seconds later, gamma-ray telescopes detected light from the same collision. The gravitational waves and light both traveled 130 million years across space, arriving within 2 seconds of each other. This confirmed that gravity and light travel at essentially the same speed. Why? Because both are propagating at the maximum speed of causality. The speed of light isn't special, because light is special. Light travels at c, because c is the cosmic speed limit, and massless particles automatically move at the speed limit. If photons somehow had a tiny mass, even an incredibly small one, they would travel slightly slower than c. Neutrinos were once thought to be massless, and scientists assumed they traveled at light speed. Then in 1998, experiments showed neutrinos have a tiny but non-zero mass. They travel at 99.99% of light speed, but not quite at c. Only truly massless particles travel at exactly c, and anything massless must travel at c. It can't go slower. Here's why. Remember that equation E equals mc squared plus pc squared? If mass is 0, then E equals pc. Energy equals momentum times c. For the energy and momentum to be real and non-zero, the particle must be moving at c. There's no solution to the equations where a massless particle moves at any other speed. This is profound. Light doesn't try to move at light speed. Light exists at light speed. The concept of light at rest, or light moving slower, is mathematically undefined. The speed limit c is built into the geometry of spacetime itself. Hermann Minkowski, in 1908, reformulated special relativity in geometric terms, showing that space and time are not separate, but form a unified four-dimensional spacetime with a particular geometric structure. In this Minkowski spacetime, the distance between two events is given by a metric that includes a minus sign between time and space. Delta S squared equals CPT squared x squared delta y squared z squared. This might look like abstract math, but it has a crucial consequence. Events separated by light, where delta S squared equals 0, form the boundary between events that can causally connect, time-like separation, delta squared 0, and events that cannot, space-like separation, delta S squared 0. Light literally defines the causal structure of spacetime by being the boundary case. And light itself sits exactly on that boundary, experiencing zero spacetime interval between any 2 points along its path. From your perspective, a photon travels through space and time. From spacetime's geometric perspective, the photon connects two events with zero spacetime separation. From the photon's non-perspective, there is no separation at all. This is why faster-than-light travel isn't just technologically impossible, it's logically problematic. If you could send information faster than light, you could create situations where effects precede causes from certain reference frames. You could send messages into your own past. Causality would break down. The speed of light protects causality. It's not a law we obey, it's a structural feature of reality that makes consistent causality possible. And yet, light itself doesn't experience this causality it protects. Light doesn't experience cause and effect, sequence, change over time. Light exists in a realm where emission and absorption are simultaneous, where cause and effect collapse into a single moment. Lee Smolin, a theoretical physicist working on quantum gravity, puts it this way: the speed of light is the most fundamental constant in physics, not because light is fundamental, but because causality is fundamental. Light just happens to be our most accessible window into the causal structure of spacetime. The universe runs on causality. Events cause other events. The past influences the future. And all of this causality propagates at exactly one speed, the speed that light happens to travel at, not because light is special, but because that speed is built into the structure of spacetime itself. Light, existing outside any frame of reference, is the perfect messenger for causality, precisely because it doesn't experience what it's mediating. Now let's explore what light's lack of a frame of reference reveals about the nature of reality itself. Physics has spent centuries discovering conservation laws, quantities that remain constant. Energy is conserved. Momentum is conserved. Electric charge is conserved. These conservation laws aren't arbitrary. They arise from symmetries in nature. Emmy Noether proved in 1915 that every conservation law corresponds to a symmetry. Conservation of energy arises from time translation symmetry. Physics works the same today as tomorrow. Conservation of momentum arises from space translation symmetry. Physics works the same here as over there. Conservation of angular momentum arises from rotational symmetry, but light breaks time translation symmetry from its own perspective. If a photon doesn't experience time, how can time translation symmetry apply to it? The answer is subtle. The symmetry applies to spacetime as a whole, not to individual photons. Light doesn't experience the symmetry, but the electromagnetic field, the fundamental entity of which photons are excitations, respects all the symmetries. Light is an emergent phenomenon of the electromagnetic field. And that field has a deep symmetry called gauge symmetry, which underlies all of electromagnetic theory and quantum electrodynamics. Gauge symmetry is abstract. It's a symmetry in the mathematical description of the field, not a symmetry you can visualize in space and time, but it's incredibly powerful. The requirement that physics be gauge symmetric essentially forces electromagnetism to have the form it does. And gauge symmetry requires the photon to be massless. If photons had any mass, even infinitesimally small, gauge symmetry would be broken, and electromagnetism as we know it wouldn't work. This is profound. Light must be massless for the universe to have consistent electromagnetism. And being massless means light must travel at sea. And traveling at sea means light cannot have a frame of reference. So light's lack of a frame of reference isn't an accident. It's necessary for the electromagnetic force to exist at all. This connects to a deeper pattern in physics. The standard model of particle physics describes all known particles and forces, except gravity. It includes photons, electromagnetic force, gluons, strong nuclear force, and W and Z bosons, weak nuclear force. Photons and gluons are massless and travel at light speed. They have no frame of reference. W and Z bosons have mass and travel slower than light. They do have frames of reference. Why the difference? It comes from spontaneous symmetry breaking. In the early, hot universe, all these force-carrying particles were massless. As the universe cooled, the Higgs field turned on, giving mass to some particles but not others. Photons remained massless because electromagnetic gauge symmetry protects them. Gluons remained massless because color gauge symmetry protects them. But W and Z bosons gained mass because the symmetry protecting them was broken by the Higgs mechanism. Peter Higgs and Francois Englert won the 2013 Nobel Prize for predicting this mechanism. The discovery of the Higgs boson at CERN in 2012 confirmed their theory. But here's the key insight. The massless particles, the ones with no frame of reference, are the ones carrying the most fundamental, unbroken symmetries. The particles with mass and frames of reference are the ones associated with broken symmetries. In some sense, having a frame of reference is a consequence of symmetry breaking. Light exists in a more symmetric, more fundamental state than massive particles. This might seem backwards. We experience having a frame of reference. We exist in time and space. Shouldn't we be the normal ones and light be the weird exception? But from the universe's perspective, light might be more fundamental. Mass, time, frames of reference, these might be emergent properties that appear when fundamental symmetries break. Some cutting-edge theories in quantum gravity suggest that spacetime itself is emergent, that at the deepest level, reality doesn't have space or time, and these emerge from more fundamental quantum information. If this is true, then light existing outside space and time might be closer to the fundamental level of reality than we are. We're the emergent phenomena, and light is giving us glimpses of the deeper reality underlying spacetime. Carlo Rovelli, working on loop quantum gravity, suggests that time is not fundamental but emerges from quantum interactions. In his view, the flow of time is a consequence of our thermal, macroscopic perspective. At the fundamental level, there's just a timeless quantum state. If time is emergent, then light experiencing no time exists at a more fundamental level. Light doesn't experience time not because it's weird, but because time doesn't exist at light's level of reality. We experience time because we're made of many particles in thermal equilibrium, with entropy increasing. We're complex, emergent structures. Light is simple, fundamental. Light sees, or rather, doesn't see reality as it truly is beneath the emergent phenomenon of time. This connects to the holographic principle proposed by Gerard 't Hooft and developed by Leonard Susskind. This principle suggests that all the information in a volume of space can be encoded on the boundary of that space, like a hologram. Black hole physics strongly hints this is true. The entropy of a black hole, the amount of information it can contain, is proportional to its surface area, not its volume. This suggests that the three-dimensional volume is somehow redundant, and the real information is two-dimensional. Light, with its light cones defining causal boundaries, plays a crucial role in the holographic principle. The boundary of spacetime, where information is fundamentally encoded, is a light-like surface, a surface that light itself would consider to have zero extent. Maybe light has no frame of reference, because at the deepest level, there's no space or time for it to have a reference in. Maybe light shows us that space and time are illusions, useful emergent descriptions, but not fundamental reality. This is speculative, cutting-edge physics, but it's where light's strange properties lead us. Light doesn't just challenge our intuitions about motion and time, it challenges the very notions of space and time themselves. Let's step back from the math and physics and ask a philosophical question. What is real? You experience duration. You experience change. You experience motion through space. These seem undeniably real to you. But from light's perspective, from the perspective of the fundamental messengers and mediators of reality, none of these exist. So which perspective is correct? Which describes reality as it truly is? Philosophers have grappled with this for millennia. Parmenides, an ancient Greek philosopher, argued that change is an illusion, and reality is a timeless, unchanging whole. Heraclitus argued the opposite, that change is the only constant, and reality is pure flux. Modern physics suggests both were partly right. From your frame of reference, with your time dimension, change is real. You age, entropy increases, cause leads to effect. But from light's non-frame, all moments exist simultaneously, unchanging and eternal. The physicist's answer is that reality is frame-dependent. There is no view from nowhere, no absolute perspective from which to judge which description is correct. Different frames of reference give different but equally valid descriptions. This is the principle of relativity. Physics looks the same in all inertial reference frames. There's no privileged frame that's more real than others. Except that light doesn't have an inertial reference frame. Light exists outside the set of valid perspectives. So does that make light's perspective invalid? Or does it make light somehow more objective, transcending all relative frames? Here's a thought experiment. Imagine a photon's entire existence. It's created in the sun's core, works its way to the surface, travels through space, enters your eye, and is absorbed. From your perspective, this takes tens of thousands of years plus 8 minutes. The photon has a history, a sequence of events in time. But from the photon's perspective, emission and absorption are simultaneous. There is no sequence, no history, no change. The photon doesn't experience its journey because experience requires duration, and duration doesn't exist for light. Now ask, which description is real? The temporal sequence you observe, or the timeless simultaneity the photon experiences? The answer physics gives is both. Or more precisely, neither description is more real than the other. Reality isn't just one way, it's the collection of all valid descriptions from all valid frames of reference. This is ontological relativity, the idea that what exists depends on your frame of reference. Time dilation isn't about clocks being wrong. It's about time itself being different in different frames. But light seems to sit outside this framework. Light has no frame of reference, yet light defines the framework. Light is both supremely important, mediating all electromagnetic interactions, defining causality, and completely absent, experiencing none of what it enables. This paradox resembles Zen koan's contradictions, designed to break linear thinking and reveal deeper truth. What is the sound of one hand clapping? If a tree falls in a forest with no one around, does it make a sound? Here's the light koan. From light's perspective, does the universe exist? If the universe is made of events in spacetime, and light experiences zero spacetime interval between events, then from light's non-perspective, all events are simultaneous and co-located. The universe collapses to a single point moment, but light mediates every interaction in that universe. Without light, electromagnetic forces don't work, atoms don't hold together, chemistry and biology don't exist. So light is necessary for the universe to exist, but from light's perspective, the universe doesn't exist as something extended in space and time. This brings us to the measurement problem in quantum mechanics. Quantum systems exist in superpositions, multiple states simultaneously, until measured. Measurement collapses the superposition into a definite state. But what counts as measurement? Physicists have debated this for a century. Some interpretations say consciousness is required. Others say any interaction with a large classical system counts. Others say superpositions never truly collapse. All possibilities exist in branching parallel worlds. Light is always involved in measurement. We measure things by detecting photons from them or scattering photons off them. But light itself is in superposition until it interacts with something else. So in a sense, light carries information about quantum superpositions while being in superposition itself. Light bridges the quantum and classical worlds without being fully in either. John Wheeler proposed the participatory universe, the idea that observers don't just observe the universe, they participate in creating it through observation. And observation fundamentally involves light. When you look at a star, you might think you're passively receiving information. But quantum mechanics says the star's properties weren't fully defined until your observation. In his delayed choice experiments, Wheeler showed that your choice of measurement can determine the past behavior of photons. The universe isn't just out there waiting to be observed. The universe and observers co-create each other through interactions mediated by light, but light itself doesn't observe. Light doesn't participate. Light is the medium of participation, existing outside the participatory framework. It's like language. Language allows us to communicate, to share ideas, to create meaning. But language itself doesn't have ideas or meaning. It's the medium through which meaning flows. Light is the language of the universe, the medium through which information flows, but it has no information content from its own perspective. The philosopher Thomas Nagel wrote a famous paper asking, "What is it like to be a bat?" His point was that subjective experience is inherently perspectival. There's something it's like to be you, something it's like to be a bat, something it's like to have any particular point of view. But what is it like to be a photon? The answer is nothing. There's nothing it's like to be a photon, because photons don't have experiences. They don't have duration in which experiences could unfold. They don't have a perspective from which experiences could arise. Photons are pure relationality. They exist only as connections between other things, never for themselves. This might be the deepest lesson light teaches us. Reality is fundamentally relational. Properties don't exist in isolation. They exist in relationships. Space and time aren't absolute containers. They're networks of relationships between events. And light weaves that network without being part of it. Let's explore the cutting edge of light research, where scientists are pushing the boundaries of what's possible. In quantum information science, researchers are using light to build quantum computers and quantum communication networks. Photons are ideal for this because they don't interact much with their environment, allowing quantum information to be preserved. In 2020, Chinese scientists achieved quantum teleportation of photons over a distance of 44 kilometers. They entangled photons, separated them, and then measured one photon in a way that instantaneously determined the state of the other. They used this to teleport quantum information not faster than light, because classical information still had to travel at normal speeds, but in a way that preserved quantum coherence over long distances. Quantum key distribution using entangled photons is already being used for secure communication. Any eavesdropping attempt disrupts the entanglement, immediately revealing the intrusion. Banks and governments are beginning to use quantum encryption for ultra-secure communications.